I'll be presenting our work on policies, automated analysis of privacy policies using deep learning. I'm Hamza from EPFL in Switzerland, and this is joint work with Qasim from Wisconsin, Remy and Carr from EPFL, and Florian and Kang from University of Michigan. So the problem we are working with is that privacy policies are long and complex. And this is how privacy policies that person uses on a regular basis compares to a person using a common American unit, which is the football field. So people do not read them. People have also tried to fix that problem before. And the approaches so far were to put more humans or more lawyers on the task. So standardization was proposed for a long time as a potential fix, using labels similar to nutrition labels. But this didn't work because it required providers to do something voluntarily without any motivation to do it. The other approach was crowdsourcing. So ask volunteers to read this privacy policy for us and explain them. Well, also this has not worked. Also for a few years, TOSDR has been available there, but only for a couple of hundred policies. Only a couple of hundred policies have been analyzed, and with GDPR, overnight they became stale. So manual work does not scale. And it also fails to cope with emerging technologies. So technologies such as screen-limited devices or voice-activated devices. So we cannot just read a privacy policy there. We cannot just rely on another device to conduct the whole process. And this kind of devices is where we can ask, for example, one solution would be to ask questions about the privacy practices and get answers instantly. But there's no way to do that. We call these kinds of queries unstructured queries because the user can ask anything they want. There's also need for more structured queries. So take regulatory compliance, for example. With a GDPR, there has become a need for regulators to sift through all these privacy policies. So what if we can provide these regulators with an interface for querying a large corpus of privacy policies, for example, for all the policies which contain statements on health data sharing? So the solution we have designed is Polisis. Polisis is a unified framework for privacy policy analysis. So our idea is that once we can automate the analysis of privacy policies on a low level, we can construct any interface on top of this analysis that we want. We don't like the interface, we change it, but we don't change the analysis itself. And this can be changed in software. So Polisis is available at pribot.org, and you can visit the site now and see any privacy policy, analyze it, and use our approaches at this point. So the framework we have built looks like this. So we have an application layer. So at the application layer, there's an app that you can query with. So for example, you can do an unstructured or structured query as I showed before. And you query about a privacy policy with a link of the privacy policy given to the application. So next, the privacy policy is broken into smaller segments because we want to analyze them in detail. Next, these segments are fed into the machine learning layer, where we pass them through a set of classifiers in order to know what is in each segment. Then the query itself is analyzed, depending on how it looks like. And finally, the queries and the query classes and the segment classes are matched together to find which segments answer the query that is given. And this class comparison is custom to the application. So to start with, I will describe the data layer. So how do we break these segments? So after we have obtained the privacy policy, whether by giving it to the user or via other automated ways of crawling the website, we pre-process the policy. Now, why we do that? We want to deal with problems like this. So take lists, for example. If I just take your real name, I don't know if this is talking about sharing this real name or collecting this real name. So I need the preceding sentence. So in these cases, we merge short lists into the preceding sentence. But if we have long lists, especially when we have nesting, we don't want to have a very large body of text to classify. So what we do is that we duplicate the preceding sentence into multiple segments. So we end up with 2 segments and the preceding sentence is common. So after that, we do coarse segmentation of the policy according to HTML tags. So think about it like breaking policy into paragraphs. Finally, we break paragraphs into smaller even entities which are semantically coherent. So these could be a couple of sentences. Okay, so this is how we do the segmentation. Now, how we do the classification. So let's start with an example. This is an example from Intel's privacy policy. So at a high level, this segment is talking about data retention because as we see, we may need to retain certain information. Now, on a lower level, there's more detail there. So the purpose for data retention is legal requirement, and the information type is generic information. It's not talking about specific data. So we have 2 levels of abstraction in each segment of the policy. And these were, this taxonomy that we have on the left has been proposed in the paper by Wilson et al. In ACL 2016. And they provided also a set of labeled privacy policies, 115 privacy policies that are labeled similar to how this segment is labeled. So the taxonomy on a broader look at this taxonomy is like this. So there's first-party collection, third-party sharing, etc. And there are these low-level attributes here, and each of them has several values. So information type is financial, health, location, etc. So given hierarchical data, we thought the best model would be a hierarchical model, or a hierarchical architecture. So our architecture looks like this. We have at the high level a category classifier that tells us what is the category of each segment. On the lower level, we have value level classifiers that tell us, for example, what is the information type. And it's important to note that this low-level classifier only makes sense if given that this is a first-party collection. So we don't care about the information type if we are talking about, for example, policy change. So they are interpreted in context of the categories. The architecture for each of these classifiers, we had 21 classifiers, looks like this. I won't enter into the details, but it is a convolutional neural network with one layer convolutional neural network. It's a multi-label classifier because a segment might have multiple types of information, for example. At the input, we have an embedding layer. Now, embedding layer represents words as vectors. I also won't describe the details of this, but the important thing to note is that we obtained a large improvement in terms of classification accuracy by pre-training these word vectors on a large corpus of 130,000 privacy policies that we crawled from the Play Store. That was the best source for obtaining a large number of policies. So that's how we classify policies. Now, I will go into more details about how we use the rest of the components here in specific applications. So the structured querying is the first category of application. As a case study, we'll take privacy icon assignment. So privacy icons have been proposed before as the alternative to privacy policies, or the alternative view to privacy policies. So there were approaches by Mozilla and by Disconnect to design icons. There is a problem in how to design the best icons, but the problem is how to populate these icons also. And that's one reason why these icons didn't take off. So we'll take Disconnect icons, which were populated by data from TrustE, a well-known compliance company, privacy compliance company. Disconnect icons had high hopes. They were used in a browser extension. They were integrated in Disconnect Search. Now, sadly, they were discontinued in 2017. You can not know the reasons why. The disconnect icons actually look like this. So we have expected use, expected collection, precise location, data retention, do not track, and children privacy. So, and there were up to 4 icons in each category. So, for example, here we had red, yellow, green, gray, with decreasing risk. So, how do we, if we want to deal with these icons with our framework to automate their assignment, how do we do that? So, we have structured queries here. So, a query looks like this. It's about defining what are the categories and what are the attributes according to the taxonomy that we have already. The query can get more complex, but this is an example. So the query analyzer is not very complex because we already have the classes in the query. We don't have to guess them. The class comparison can be done with first order logic. So find these segments with the given conditions. So to give an example, this is expected collection. So does this website's privacy policy disclose whether it allows other companies, so that's third-party sharing or collection in our labels, like ad providers and analytics firms, so that's purpose advertising or purpose analytics research. Then track users on the site, so we had also labels for that. And the yellow icon, which we have as an example here, is basically having opt-out choices. So in this case, we were lucky that we had an exact match from all the language that disconnect icons used to our case. But the purpose of this was to show if we have a plausible interpretation of these icons, can we automate the assignment in an accurate way if our explanation is fine, or if our interpretation is acceptable. Because disconnect icons are not like provably the best icons that you can do. You can always do something different. So given these structured queries, given these rules that we had set, similar to this query, for example, we ran these rules over 50 policies from the OPP 115 data set that we didn't train our machine learning on. We assigned first the icons based on the labels in this data set, which were done by law students. So third-party sharing, collection, or advertising were set by the law students. The rules were set by us. And then we compared that to icon assignment with these rules based on Polisis labels. We obtained 88.4% accuracy across the icons in matching the icons based on law students' labels. So this shows us that we can automate the assignment of icons with acceptable accuracy using our system. And to also put this number in context, 88.4% accuracy is close to the agreement level between different human judges in similar scenarios. So we're not saying it's perfect, but not only machine learning is not so accurate, also humans disagree, lawyers especially. So unstructured querying is the second application. We take answer selection as the case study. Answer selection is basically question answering with answers which are predefined. So do you share my address with other companies? Our goal was to find the segment in the policy which answers this question if it exists. So similar, we use our framework. We have the query as an input. And we have the query analyzer as a machine learning classifier this time because we don't have the classes in the question. For the purposes of this presentation, you can assume that the same classifiers apply to query and the segment. Finally, we have, after we pass the classifiers, the queries into the classifiers, we have a comparison. What are the segments matching this query? So we had a custom class matching function for that. Remember, if you want to do this with machine learning end-to-end, you could also train a question answering system end-to-end. But we don't have questions and answers data set, and we want to do the whole thing within our framework. So we did the following. So given the queries, given the query and given the segments, we first classify the query according to the different classifiers. We have two levels, the category level and the value level, CI and VJ here. So the answer vector, for each answer we give a vector. It's similar to a joint probability, but we put more weight on matching categories or non-matching categories by having a square here. So it's the similar query vector for the question. So intuitively similar vectors have more likelihood to be answers to this. Answers with similar vectors have more likelihood to answer this query or this question. And then what we do is that, given the alpha and the beta, the vectors, we compute the score between the question and the answer according to that function. The idea behind that function is that we want to prioritize the answers that include questions classes with high probability, but we don't care if the answer has more details. We don't want to match exactly what is in the answer. We just want to get the answers to match the question. So it's like an asymmetric version of a dot product. And then we had some normalization factors and some certainty metric to say, is this answer classified? How sure are we that this answer is classified according to the labels that we have? So the evaluation baselines to compare against were the BM25 model, which is the state-of-the-art in term matching, the semantic vector model, which is a baseline we developed in order to have a flat hierarchy instead of a hierarchical architecture. It's also a neural network classifier with a similar architecture. And finally, we had a random answer model that just gives random answers from the policy. In order to assess these models, we had to get a data set of questions. The best way to get unbiased questions is to find already asked questions before. So we went to Twitter, but instead of searching for questions and biasing the data, we searched for answers that look like, go check our privacy policy. So what we did is that we backtracked them into the questions, and these questions are typically about the privacy policy. We did also some annotation to filter out the ones which were not. We ended up with 120 questions. So we evaluated our models according to predictive accuracy and user perceived utility. Predictive accuracy compared to expert answers, and user perceived utility, we did a user study in order to assess the quality of these answers. So I will talk about predictive accuracy. So what we do is that, given these answers that we have from the segmenter, ask experts what are the answers to a given question, so A5 and A11, and with each ranking model get the answers also. And the question is, how many of these questions have an expert answers in top K? So top 1 means that we got the first answer as correct. Top 3 means one of the first 3 answers is correct. We found that in our hierarchical model, 82% of the questions had an accurate answer in the top 3. And that was lower for other models. It was even more significant at 1. We had like around 68% top 1 accuracy. And the differences become higher for lower for higher K, but we are interested in matching at lower numbers of K. So that's it. That's unstructured queries part. So finally, I will finish with a demo, but you can find more on pribot.org. So this is a demo of how we use structured querying to visualize privacy policies. In this case, the data collection, what types of info is collected, collection reasons, and what choices are given. So for example, you can go to the website, you can hover over each link and see what are the segments about this type of information. And you can see, for example, what are the statements about children data collection, etc. You can also ask questions to our chatbot about a certain privacy policy. Any question, we will try to find if it's about privacy policies. There's also some experimental features, like simplifying the answers. It's not yet ready there, but you can test it. And we are working on other additions soon. So coming soon is like an interface to get like just what you want from the privacy policy. What's good, what's bad. So for example, Yeah, in certain conditions, data is not shared. This is the evidence. And in certain conditions, data might be retained indefinitely. So we had so far more than 35,000 users of the app, 88,000 minutes spent on our apps, and users and us have added more than 21,000 policies already. So that's it. Policies is a unified framework for the analysis of privacy policies that is potentially beneficial for users, regulators, and researchers. It supports structured and unstructured querying, and you can find more in our paper or at pribot.org. Thanks for your time.
Couple minutes for questions before our session is over. Okay, while you're all rushing to the microphone, hi, Michael.
Oh, I found it interesting that your system wasn't completely accurate, but neither were humans. Could you do something like agnostic learning to label parts of privacy policies as just incomprehensible?
So by incomprehensible, you mean like what? Generic or like?
That your system can't figure out whether something's true or not. For example, you're trying to answer queries, but you could both try to answer the query and then also characterize how confident you are. And if it's really incomprehensible, that might be characterized as a coin flip.
Mm-hmm. So we can get an assessment of how confused our classifiers are by taking the entropy of the class probabilities, but we cannot be sure that this is resulting from the text itself being incomprehensible or by the limitations of our data. So although there are other ways to judge how incomprehensible by seeing, for example, using readability metrics to see, let's say, that the text is something that only a university student can read, and these do not use machine learning, they just use word statistics. These could be more tailored to do something like assessing incomprehensibility if you want.
Thank you.
So it's a neat idea to look at existing questions on Twitter to then guide how your queries might come in, or what sorts of questions you might need to answer. I wonder, with your demo available on your website, have you collected enough questions to then be able to compare back to see what sorts of queries do people ask when they have your tool?
So yeah, we have the data set of all the questions that have been asked in our system. We didn't have like a feedback mechanism to judge the quality when we launched the system. That would have been very helpful in order to train our classifiers from scratch on question answering. We didn't have that, but we have the questions data set. So we are able to use that to inform, for example, we can use that to inform what is missing from privacy policies. Yeah. So what is the thing that users are asking, but it's not present there. So yeah, we can do that at this point.
Cool. That'd be neat.
Often these machine learning classifiers are susceptible to noise. Like if you just, because in images also it has been shown that if you add a little bit of noise, the classifiers are totally classifying it wrongly. So how do you try to handle that situation if the text is like written in such a way that the classifier is...
Yeah. So our classifiers are really not perfect, but that's the case for all natural language processing classifiers. So, and especially when we have limited data. So we already have the problem that we cannot be perfect at this point. Now, regarding the noise, there are two types of let's say, regarding the inaccuracy, there are two types. One which is due to the classifier being not well trained or not enough data, and the other being to users doing some malicious changes to the privacy policy. So if users do some intricate changes to the privacy policy, like by changing words into remote synonyms that have the same meaning, but we didn't have them in our data, that is possible to reduce the quality of the classifier. But that has to be a really targeted attack. And when this happens on a scale, that means that our system is already like really successful, that it is being attacked, and this is a good problem to solve at that time.
Thank you. So let's thank all of our speakers one more time.